Hi, it's Matt, and in this video we're going to talk about how to construct the overlap matrix. If you've already seen my video on how to construct the Hamiltonian matrix, you'll find this one to be pretty similar. So first, we're referring to the overlap matrix S. It's going to have this form. So S is going to be equal to a matrix where we have matrix elements S11, S12, S21, etc. And remember that the first number subscripted is going to be the row, and the second number subscripted is the column. So for example, this element here, S21, that is the element in row 2, column 1. And then I expanded it out into the bracket form because we know that the matrix elements are given by Sij is equal to the bracket integral across all space of chi j. Again, comparing this to the operator matrix, you'll notice that this is essentially the same, but without the operator in the middle. And the matrix will always be symmetrical about the long diagonal, so chi j is going to be equal to chi j chi. So if I draw the long diagonal in this matrix, we'll find that, for example, the integral of chi2 chi1 will be equal to the integral of chi1 chi2. And lastly, if all of our basis functions are orthogonal, we're going to get the identity matrix. Specifically, if we get the ones, that means we're in an orthonormal basis, which typically in quantum mechanics, if our basis is orthogonal, we'll typically also be using one that's orthonormal as well. And in this case, we get that chi j equals 0, and this is so long that I does not equal j. So now let's do an example where we're actually just given the matrix elements and we just need to piece together our matrix. So we're going to build the overlap matrix for basis functions chi1, chi2, chi3, and we're going to be given the following information. So again, I'm not going to read out all of these, but let's take a look. So since we have 3 basis functions, our overlap matrix is going to be a 3 by 3 matrix. So again, if we have n basis functions, our overlap matrix will be n by n. So we're given that the integral of chi1 is equal to 1. So here we have I equals 1 and j equals 1. So this will be row 1, column 1. So we're just going to put a 1. We're told the same thing for chi2 and chi3. However, in chi2, the second one, I is equal to j is equal to 2, and similarly for the third one, except it's 3. So in row 2, column 2, we're going to put a 1, and then because we have chi3 is equal to 1, in row 3, column 3, we're also going to have a 1. So now we're going to move on to our off-diagonal elements, such as chi1, chi2. So this would be I equals 1, j equals 2. So this would be in row 1, column 2. We have that the value is 0.5. Next, we're told that chi1, chi3 is 0.4. So again, that's I equals 1, j equals 3. So row 1, column 3, we're going to have a 0.4. And then finally, we're told that chi2, chi3 is 0.3. That's going to be row 2, column 3. But now we see that our matrix is only a little bit more than half full. And how we get those other elements is through symmetry. Remember that when we reverse I and j, the value of the integral remains the same. Or we could also think about it as it being symmetrical about this long diagonal. So removing that I'm going to leave that long diagonal there, but remember that everything on each side of the diagonal should be equal. So if chi1, chi2 is 0.5, then chi2, chi1, so row 2, column 1, should also be 0.5. And then by symmetry, we'll get that the bottom left is equal to the top right, so 0.4. And then we get that chi2, chi3 will be equal to chi3, chi2. So this is our final overlap matrix, and I'll also remove that diagonal. So now, sometimes we may not be given the matrix elements, and instead we'll just be given directly the basis functions. So how do we handle it in this case? So if the matrix elements are not directly given, but we're given the basis functions, we're going to have to manually compute the integrals. And to do that, let's remember the meaning of the bracket notation. So if we're given in the bracket notation the integral of chi I chi j, that's going to be equal to the integral across all space of chi I chi j d tau, where d tau just represents all of our coordinates. So in one dimension, we'll call this dimension x, and if we want the integral of chi 1 chi 2, that would be the integral, again, across all space, all of chi 1 times chi 2, and then we would just have dx. So now, let's do an example of this, where we're asked to construct the overlap matrix, but we're given the basis functions instead of the matrix elements. So here we're given chi 1 will be sine of x from 0 to pi over 2, and chi 2 will be cosine of x from 0 to pi over 2. And again, these are not necessarily valid in quantum mechanics or good basis functions. They're just here for example sake only. So what I'm going to do is we're going to move to a new slide and we're going to manually compute these elements. Note that I'm not going to fully explain how to calculate the integrals here. I'm just going to be using an integral calculator, but because I really want to focus on the construction of the matrix. If you have any questions on how I computed these matrix elements and how you would solve the integral by hand, feel free to leave a comment below. So now, since we have two basis functions, we know that our overlap matrix is going to be a 2 by 2, so we're going to need 4 elements, our S11, S12, S21, S22. Let's start by finding the S11. So S11 in bracket form is going to be the integral of chi 1 chi 1. When casted to an integral, that's going to be the integral from 0 to pi over 2 of, we're now going to fill in for chi 1, which we're told is sine of x. And now we multiply it by, again, chi 1, which we're told is sine of x. And then adding our differential dx, this integral will give us our S11 element. Using Mathematica, we find this integral to be pi over 4. Now we're going to move on to the next matrix element, which is S12. And that's going to be equal to the integral across all space of chi 1, chi 2. And that's going to be equal to the integral, again, across all space of 0 to pi over 2. We're going to plug in chi 1 as sine of x. And we're going to plug in chi 2 as cosine of x dx. Note that we're only integrating from 0 to pi over 2 here because the wave function is 0 everywhere else, so it wouldn't contribute to the integral. And using an integral calculator, we find that this integral is equal to 1/2. Now we want to find our S21 element. And we could go through, put in the bracket notation, then create our integral, but there's an easier way here. Again, by symmetry, we know that flipping the I and j value doesn't affect the value. So if S12 is 1/2, we'll know that S21 is also 1/2. Finally, we need to find the S22 element. And cast it into the bracket notation, that's going to be bracket chi 2, chi 2. And this is going to be the integral from 0 to pi over 2. We're going to plug in chi 2 to be cosine of x. We're going to then multiply by, again, chi 2, which is cosine of x dx. And plugging this into an integral calculator gives us pi over 4. Note how here S11 and S22 are equal to each other. That will not always be the case, and that's just a coincidence because of what functions I chose. Also, as a final note, some of you may have noticed that when I took the bra of chi 2, I just wrote it as cosine of x, or chi 2, rather than the complex conjugate of chi 2. Technically, that conjugate is there, but most likely we'll be using real basis functions, or basis functions that are always real valued, so we were able to drop the conjugate. If you did have a basis function that was complex, you would need to take the complex conjugate when evaluating the integral. Nonetheless, now that we have our 4 matrix elements, we can assemble our overlap matrix S, which I'm actually going to write in yellow here. So we find that our overlap matrix will be, in the top left, we have S11, which we found to be pi over 4. In row 1, column 2, we'll have 1/2, as that's S12. S21 is 1/2, and then finally S22, our bottom right element, will be pi over 4. And this here will be our overlap matrix for these basis functions.